So let's start working on the K1 lesson. And actually, I think I have this on one of the videos anyway. So we have a new fertilizer has been developed by the graduate students. I'm going to probably have to duplicate this, ignore it. Just so I can look at data. You're like, why are you duplicating that, Mrs. Everman? She likes to see the data when she's typing things in. So anyways, we've got a new fertilizer has been developed by the graduate students in the plant sciences department at your school to increase tomato yield. They decide to test the fertilizer by measuring the number of tomatoes produced by 8 plants, applying fertilizer, waiting 2 weeks, and measuring the number of tomatoes produced by the 4 plants again. The data they obtained are provided below. Do the data indicate that the number of tomatoes produced by the plants increased? Use alpha as 5%, and we're going to have the difference is B minus A, so before minus after. So that would be here. And we are wanting to know that do the data indicate that the number of tomatoes increased? So why am I looking at that? Because I'm looking at the null and the alternate. So first of all, the null is that the mean difference is going to equal 0. It could be that one. It could be that one, or it could be that one, right? It could be any of those 3. But we want to know if it increased, so that means the difference is greater than 0. What sampling distribution will we use? Well, we have means, and so it's a student T. The normal is for proportions. Student's T is for means. Not for tomato, but means. All right. And we've never deal with a uniform distribution. It's an approximately normal distribution. All right, then they say, oh, what's the value of your sample test statistic? So let's make sure we've got all this correct first. All right, and there we go. We have all the right answers. Now we got to do some data. So I just have to look at this row of data. So I'm going to go ahead. It's one. What kind of data is it? They're all numbers. All right, so it's not counts. It's the amount of tomatoes increased. Now it could feel like counts. I could see that. But we're taking 2 numbers, subtracting them, and getting another number. And so the negative signs are important too. So I want one quantitative variable, and we're going to call this change in tomato yield. You don't have to do that. And I'm just basically typing in the numbers on the bottom row. And I hit begin analysis. So you should feel pretty comfortable in this, because when we do this paired difference, this is a paired difference. Read. We do, do we do before minus after? Tomatoes before. Oh, I think I have a typo. Oh, well, so we're going to assume these are the right numbers. That should be a -5. Oh, wait. It's after minus before. So I just have a typo right here. I have to say after minus before. I'll fix that, so you'll never go, Mrs. Zimmerman, what are you talking about? It says after minus before. I have many powers, but not to turn back time on a video. Well, I could. All right, so we have our data there, and we come and we begin our analysis, and we're going to slide down to the perform inference section. We're doing a test, so it's a one sample t-test for mu. And our hypothesized mean is that the difference is bigger than 0, because we think the fertilizer is going to improve the yields. So I'm getting 1.4884. Boom. Then the p-value is 0.0901. There it is. So let's go ahead and hit submit, make sure. And voila, that's it. So if I had to come to a conclusion, I'm like, p-value, not that low, not that impressive. We probably think, the fertilizer, not that great. All right, part 2, some review of older material. Given that IQ scores are approximately normally distributed with a mean of 100 and a standard deviation of 15. So that means I'm going to go to my handy stapplet. All right, and we're doing the normal distribution. All right. And they said the mean was 100 and the standard deviation is 15. 100, 15. And what do we want to know? The proportion with IQs above 130. All right, so to the right of 30, calculate area. Ooh, no, not 30. hopefully you have people have higher than a 30 IQ. 130, 2.28% or 0.0228. And that's bad. Oh, this is probably using the empirical rule. I'm going, why is it 2.5%? This, remember, if we have more than 2 standard deviations above the mean, that's 0.5%. So that's where that's coming from. That's why it says 2.5% instead of the 2.28%. Okay. In 1923, Babe Ruth had 522 at-bats with 205 hits. Assuming that the binomial distribution can be approximately applied, find the expected number of hits in 529 at-bats. So, first of all, had 529. So it had 5 with 205 hits. So we need to find the proportion. You know what? I'm going to do a Cami for this just to make it a little bit easier. And I'm going to grab this screen and get this problem. You won't really need this Cami. All right. Yeah, blank page. There we go. This is K. We'll call it, actually, we'll keep this Cami, and it's K Reflections scratch paper. All right. So let's paste this problem here. All right. Looks awfully tiny, doesn't it? Okay. It's a little tiny. All right. So let's find out the proportion he actually hit. So the proportion he hit was 205 hits out of 522 at-bats, and I'm going to just go Google Calculator. 205. 522, right? Make sure I did that right. 205 out of 522. Yep. 0.3927. All right. Pretty sure after rounding. Yeah, 0.3927. All right. What is the expected value for 529 hits? So it should be, by the way, it should just be a little bit bigger than 205, don't you think? Expected value equals the number of attempts times your P, right? So we're going to do 529 hits this time, times 0.3927. And I bet you it's that 208. Let's go see. So I'll just take this number and multiply it by 529. Yep, pretty much 208. So we'll go back to our problem. We're going to say 208. And look at that. We have all our points except for the last one. Please tell me if you struggled with anything or you're like, oh, this was easy, Mrs. Zefferman. I love stats and I'm telling everyone else to take it. Talk to you later.